Hey folks, hope you're all doing great. Welcome to another session on quantum physics. Now, this would be our third session uh, on quantum mechanics, and from this session, I will start developing the necessary mathematical tools that you would need in order to get started with quantum mechanics. Now, the main objective here is not just presenting a bunch of mathematical equations. Or what I intend to do is to show beyond those equations. I want you to understand the meanings of those equations, and if you get a firm understanding of them and the concepts that I'm going to introduce, then you should be ready to do quantum physics. Now, today we are going to focus on the theory of probability for discrete variables. Now, discrete variables are variables that come in chunks and they are discretized. They don't form a continuum, and you can assign whole numbers to them. Now, why do we start from the theory of probability? Is because if you recall from our first session, uh, we looked into the various schools of thoughts of quantum physics in order to interpret what the Schrodinger equation gives us. And it was at that lecture in which I explained to you that the best explanation about the wave function is given through Max Born's statistical interpretation. Just basically, it says that the wave function, or to be more accurate, the square module of the wave function, gives us a probability distribution. And once a measurement is done, then based on that probability distribution, you may end up with a particular result. And well, mathematically, and in one dimension, let's say if I have a probability distribution like this, the shaded area would give us the probability that a measurement on the position of the object, which is shown by the x-coordinate here, would be found somewhere, let's say the particle between A and B. In the language of mathematics, that is just basically a ordinary integral, a definite integral between these two limits of the square of the module of psi, the wave function. Now, because of this, we have to learn a little bit about the probability theory, and I would like to start with a quote from the Scottish mathematician and physicist James Clerk Maxwell. He famously mentions that the true logic of this world is in the calculus of probabilities. Now, if you think about this carefully, you would realize that it does actually make sense. Whenever you want to make a decision, you look into the possible outcomes. Whenever we want to take a measurement, or we want to predict something, we have to look into all the outcomes of the result. Now, as I said, I can talk for hours about this sentence, but the importance of James Clerk Maxwell is just beyond what he did or what he gave us in terms of probability or statistical physics. His most important work was his work on the theory of electromagnetism, namely these four equations, which we know as Maxwell's equations. Now, in future videos, I may start a series of lectures on electromagnetism, but for the time being, this is irrelevant. The reason I just brought these equations is to show you that they were the greatest scientific triumph of the 19th century. In fact, Richard Feynman famously says that in many years to come, perhaps hundreds or thousands of years to come, the 19th century would not be remembered by, for instance, the Civil War or let's say, other, political or economical, developments in the world, but it would most likely be remembered by the union of electricity, magnetism, and optics through Professor Maxwell's work. Now, because probability plays such a central role in modern physics, today I'm going to start by looking at a very simple example just to make things clear. And I'm going to be following the footsteps of David J. Griffiths. He's an excellent science educator. In particular, he's an excellent physicist. I will introduce him later, but the main reference that we are going to use is from his textbook on quantum mechanics. Now, we will start the theory of probability by considering, as I said, discrete variables. And I'll do that through a simple example. So let's say once you get familiar with the terms of probability theory, then you should start developing the tools that you need in order to approach quantum mechanics. So here's the simple example that I'm going to walk you through. Let's say I have a room here which is full of individuals, and each individual has a number assigned to him or her. This number actually gives the age of the individual. So you see a bunch of young people, probably young students, that are inside a classroom. And one can just, by looking at this schematic figure, you can see that there's one person age 15, one person age 14, 3 people are aged 16, and then 2 people are aged at 22 years, 2 people are aged at 24, and finally 5 people have the age of 25. And now, I can show this mathematically by developing a notation, and instead of writing it down like this, I can say, all right, n represents the number of students or people with the age j. J is my discrete variable. You see, the age is given as a whole number. I'm not talking about the exact age of the students in this classroom, but just the integer whole number that represents their age. So n is our is the number of individuals with the age j. Now, so with that notation, then I can actually say that the number of students with age 14 would be 1, and likewise the number of students with age 15 is 1, number of students with age 16 is 3, number of students with age 22 is 2, number of students with the age of 24 is 2, and there are 5 students with the age of 25. Now this notation also allows us to talk about students or ages that don't appear here in this selection of individuals. So the number of students at age 17 is obviously 0. Now, the total number of students in the room is just basically the sum of the numbers of students with a certain age. And in general, this sum can go all the way to infinity, and you can actually, develop a compact notation for the number of total individuals. So n is the number of total individuals, n of j is the number of individuals with the age j, and this sigma is the summation symbol, which just simply says that sum up all of these ages. Okay. For example, in our particular distribution of students, the total number of individuals is 14. If I sum up all of these numbers, I'll end up with 14. All right. Now, in order to analyze this distribution of students, I would use what is called a histogram. And here on the horizontal axis, I represent the age. On the vertical axis, I represent the number of students. So the number of students at age 14 is just 1. At age 15 is also 1. At age 16 is 3. At age 22, you can see it's 2. At age 24, it is 2. And at age 25, there are 5 students in the room. Now I'm going to introduce to you some important definitions by using this histogram here, and I'll do that through a number of questions. So for instance, let's say our first question is, what is the probability that if I choose a student randomly from this group, I would end up with an age of 15? So the answer to this is easy. There is only one student out of 14 students that has the age of 15, and thereby the probability would be 1 in 14. Notation-wise, this is how I would show it. P stands for probability. The probability of finding an age 15 is 1 over 14. Now, in general, the probability that a random selection would yield the age j would be shown by P of j. So it will be a function of j, right? Now, in this case, this P of j would be actually defined as the number of students in that age, j, divided by the total number of students. That's what we did right here. So the probability of finding 15 is the number of students at 15, which is 1, divided by the total number of students, which is 14 here. In other words, I can, rewrite this definition of probability in this way: the number of students with the age j over the total number of students in the room. So if I look carefully at the histogram, then I would find, let's say, the probability of finding a student at age 14 is 1 over 14, because there's only one student at age 14. Likewise, as we looked into it earlier, the probability of finding a student at age 15 is 1 over 15. The probability of finding a student at age 16 would be 3 over 14, so it's more probable to find a student at age 16 here. And you can see that this is given by a larger height here. The probability of finding a student at age 22 would be 2 out of 14. At age 24 would also be 2 out of 14. And finally, at age 25 would be 5 out of 14. So if I choose a random student from this classroom, I'm likely to find the student to be at age 25, because that is the highest probability. All right. Now, another question to be asked here is, what is the probability of getting 2 ages, either 14 or 15? Well, that would be just simply the sum of the probabilities of getting 14 and 15, which in this case would be P14 plus P15. The probability of getting 14 is 1 over 14. The probability of getting 15 is 1 over 14. And their sum would be 2 over 14, or just 1 over 7. Now let's generalize this question and ask, what is the probability of getting some age? Any age. Okay, as you may have guessed, that would be 100%, or 1, because students must have an age. Okay? It doesn't make sense of talking about a student that doesn't have an age. So if I pick a random student from this collection of students, I'm certain to get a specific age. So the answer would be the sum of all probabilities, which is 1 or 100%. So you're certain to get some age, and mathematically that would be shown by this equation here. So P of j is the probability of getting age j, and the sum over all ages would inevitably lead to 1. And if you want to find the proof, well, you can just use the definition of the probability at age j in this way, and then do the math. You can see that this sigma notation applies to the numerator, and it turns out that the numerator would be exactly equal to the denominator, so you can cancel them and you end up with 100%. All right, looking back at our histogram, now I raise another question. What is the most probable age that you can see? Well, as we discussed before, the most probable age would be the age in which I would have a higher probability to end up with when I select the individual. And looking at this histogram, it's 25. So the maximum in my probability distribution would give the most probable age. So that was easy by looking at this Instagram. So P25 is the number of students at 25 divided by the total number of students, which is 5 over 14. So in general, the most probable value is the value in which the probability distribution becomes maximized, so it takes its maximum. Another question to be asked is, what is the median age? And the answer to that is 23. Now you see there are no individuals with the age of 23. So what do we mean by median? Well, if I look carefully at this histogram, I would see that the number of students with ages smaller or less than 23 is exactly equal to the number of students having an age greater than 23. So there are 7 students younger than the age of 23 and 7 students above the age of 23. That is the concept of median. Okay, mathematically, if I want to show that, I would say the median value of a probability distribution is that value, that I, in which the probability of finding individuals with an age or with a number less than j would be exactly equal to the probability of finding students with a number greater than j. So this is the criterion, mathematical criterion of the median age. All right, we're still not done. Now we want to raise another question. What is the average or mean age? Now, usually people mistake average with median. Here I would show you how to calculate the average. There's a difference between the average and median. The average, as you probably all know from high school, is given by multiplying the age by the number of students, summing them all up, and dividing it by the total number of students. So I have one student at 14, so 1 times 14, and then one student at 15, 1 times 15, 3 students at 16, 3 times 16, 2 students at 22, 2 times 22, 2 students at 24, that will be 2 times 24, and then 5 students at 25, 5 times 25. You sum them all up and then divide by the total number of students. That would give you the average or the mean. So the average turned out to be 21, whereas the median was 23. Now there's something interesting here. Neither the average nor the median are ages in which any of the students have. So in general, the average number and also the median number need not to be in the distribution itself. So notation-wise, the average value of j is shown by j within these brackets. This is how we would show the average, and this is how we would calculate it mathematically, just like we did here. You sum up the product between the age and the number of individuals in that age, sum them all up, and then divide it by the total number of students or the total number of individuals there, and that would give you your average. Now, I see here that nj over n appears. So nj over n was p, was the probability, and then that is multiplied by j. So another way of taking the average is to multiply each age by its probability and then sum them all up. That will give you the same average value. Now, as I said, in general, there's no need to be any individual with the average value or with the median value. Okay, in our example, as we saw, the average value was 21 and the median value was 23, and no student had these ages in our collection. All right. In quantum physics, the average is what we call the expectation value. So in the language of quantum mechanics, the average of a distribution, of a probability distribution, is the expectation value. But this is a sort of sloppy language because expectation value doesn't mean it's the most probable value. But I guess we have to live with this. This was there from the definition from the beginning of literature in quantum physics, and it's just a misleading term. But you shouldn't, confuse this with the most probable value. The expectation value is the average, whereas here the most probable value was 25. Okay. Another question, what is the average of the square of the ages? Well, according to our definition, all we have to do is we have to multiply the number of individuals to the square of the ages and then sum them all up. Now, if I do that for this particular distribution, I'll end up with a number close to 460. Now, why is the average of the square of ages important? You will see in a few minutes. But this is just to give you an idea how to take averages of various quantities. Now, mathematically, this would be the sum of the squares times the number of individuals with that particular age divided by the total number of the individuals in the room. And again, since the sum of nj over n appears, this nj over n is probability, so I can actually look at the average value of the square of ages and calculate that by multiplying the square of the age times the probability of getting that age and then summing up over all the individuals in the room. So it's quite easy. Now I can generalize this idea and not only talk about the average of j or the average of j squared, but the average of any function of j. And based on my notations, the average value of any discrete function of any function of a discrete variable j would be given by that function times the probability summed up over all the individuals. So this is a very powerful equation that gives you the average of not only the individuals, but any function of the individuals in your distribution. So you can think of these special cases. For instance, if that function is 1, if I plug in 1 here, I would end up with the sum of all probabilities, which earlier we mentioned, that should be 100%. So the average value of 1 is just 1, we know that. The average value of j, if the function is j, was what we saw before. It is the sum of all j's times the probabilities. And if f of j is j squared, the averages of j squared would also look like this, as we saw in the previous slide. So you can put in any function of the discrete variable in this equation and calculate its expectation value or its average value. There's one important point to mention, and that is that the average of the squares is not necessarily equal to the square of the averages. This is also something that students sometimes get confused with. So in this first quantity, what we are doing is we are taking the squares of the ages of the individuals and then taking the average, whereas in this case, I'm just taking the average of each individual and then squaring up the result. And as I said, these two are not necessarily the same. So remember this. Through an example, I can actually show this to you by mentioning that you can do the calculation yourself. So if I have a room containing only 2, let's say babies now, aged 1 and 3, then the average squared is 4, but the average of the square is 5. So you see, they're not necessarily the same. The next important thing to talk about in the theory of probability with a bunch of data points is the spread in a distribution. Now here, let's look at these two histograms here. Well, they obviously look different, but if I calculate those quantities that I mentioned earlier, you would see that all of them have the same value. So for instance, in both these distributions, we have the same median. We have the same average. We have the same probable value, and we even have the same number of elements. So all of those important definitions in the theory of probability, which I mentioned earlier, if I calculate them for both of these distributions, I would end up with the same results. So how can I really distinguish these two distributions? Well, by just looking at the these set of data points, these histograms, I can realize that the left distribution is highly peaked about the average value, whereas the right distribution is spread out. It is completely broad with respect to the average value here, which is 5. Now, so that, makes the spread of a function being an important quantity, a spread of a distribution being an important quantity. And I want to find a way to measure the spread in a distribution. If I find that a technique to measure the spread in a distribution, then I can talk about a sharply peaked distribution and distinguish it from a rather broad distribution. So the average, the median, the most probable value, and the total number of elements, they are not enough in order to really understand qualitatively what a distribution of entities would actually give us. So, and that is very important. And that brings us to two important definitions, the variance and the standard deviation. So maybe our first attempt to understand the spread of a probability distribution is by calculating the deviation from average. The deviation from average, I will show it by delta J, and that just tells us how much an individual, the individual's age, differs from the expectation value of that individual. So that's just defined by simply subtracting the average value of the age in a group, or the average value of a probability distribution from each individual data point. And if I do that, then perhaps I can take the average of this deviation, and that can correspond to the spread of my distribution. But there's a problem here. If I take the average of the distribution, I get this guy here, the expectation value. And if I want to take the average of the deviation from the average, I would always end up with 0. And the reason for that is that delta J, calculated for all of the individuals in my specimen, is as likely to be positive than being negative, and therefore they would cancel each other's effects. So this wouldn't get us nowhere. If I want to talk about the spread of a distribution, it's not enough to just take the average of the deviation from the average, because that always is guaranteed to give me 0. What I would do instead, and here's the calculation just to show you how it becomes 0, right? The average of the deviation from the average, according to this definition, would be this. Now the average of J here, and the average of J is just the average of J, so you would end up with 0. Now, one way to get around this problem is to compute the average of the square of the deviation from the average. In that sense, I'm always going to end up with a positive number. And maybe that will help me understand or get a sense of the distribution spread. So here's the definition. Sigma squared is the average of the square of the deviation from the average. Well, this is a long sentence, right? It's a long definition. So we give it a name. We call it the variance of the distribution. And if I take the square root of the variance, in other words, if I take the square root of the average of the square of the deviation from the average, you see how difficult it sounds, that would be called the standard deviation. And this is the important parameter that we are going to use in order to understand the spread of a probability distribution. So if a probability distribution is highly peaked, that means the standard deviation would be small, because most of the individuals would be close to the average value. But if on the other hand, if the probability distribution is broad, then the standard deviation would be a large number, because each individual would be highly likely to fall in a region that is away from the average value. So this is the key quantity that we will use in order to analyze and talk about the spread in a probability distribution. All right. In other words, the standard deviation is a customary measure of the spread about the average value of the discrete variable j. All right. Now, based on this, I'm going to introduce a very useful theorem of variances. So let's say we start with the variance, which is the standard deviation squared. So if you recall from the previous slide, the standard deviation squared, or in other words, the variance, is the average of the square of the deviation from the average. So I'll just take this deviation from average and I'll replace it by what it is, j minus the average of j. Then I'll have to square it and then take the average of the entire thing. So binomial expansion, right? It's the first term squared plus the second term squared minus twice the first term times the second term. Now, I have three terms here, so I can just separate them. So here I have the average of j squared minus the average of 2 times j times the average of j, and then plus the average of j squared. I'll keep the average of j squared as it is. Here, if I apply this average, operator on this term here, 2, the average of 2 is just 2, it comes out. The average of j is j, and then the average of j is just the average of j, because the average value is always a constant. So the average of a constant is itself, okay? So that's why we have minus 2 average of j times average of j. And likewise here, we have the average of the square of the average of j. Well, the average of j is a constant, so its square would be a constant. So it doesn't make sense to talk about the average of a constant number. It is just itself. Now, here I have minus 2 average of j squared plus an average of j squared. So that gives me a minus average of j squared. And then the first term, of course, is the average of j squared, right? So the variance of my distribution, instead of, dealing with this long procedure here of calculating the deviations from the average and then squaring them and then taking those average, it's just basically found by using the average of the squares minus the square of the averages. Okay, that's why in my example I also calculated the average of the squares for the distribution in the room. So that sounds easy, and in fact this is a very powerful theorem. So the standard deviation can be now represented as the square root of the average of the squares minus the squares of the averages. Okay, now as you can see, the square root, whatever's underneath it, must be a non-negative number, and that's why the average of the square must be always greater than or equal to the square of the averages. Remember, in a few slides earlier, I mentioned that the average of the squares is in general not the same as the square of the averages. Now you see why here. Because whatever's underneath the square root sign must be positive in order for this guy, the standard deviation, to make sense. The only time in which the average of the square matches the square of the average is a distribution in which you have no spread at all. That simply means that every member in the distribution has the same value. You can check it out for yourself. So I think that would be it for this session here. So the references that I've chosen are from, it was mainly from Introduction to Quantum Mechanics, its second edition by Professor Griffiths, which here we have a picture of him. And he has a couple of standard textbooks on physics, one on particle physics, one on quantum mechanics, which is the one that we're going through, and there's another one on electrodynamics. So probably in the future, if I decide to make videos on the electrodynamics or electromagnetism, I would also use his textbook as a reference. Other than that, I've used images. Some of the images are found from the online free encyclopedia, Wikipedia. And I hope that, you know, although this lecture or this session contains some mathematics, but the mathematics is actually not that difficult. Okay, so you can always rewind this video to a slide or to a point in which you may find it challenging, give some thought, listen carefully to what I teach, and you should be completely fine. So the theory of probability for discrete variables is much more richer and much more broader than what I just mentioned in this short video. But basically, this is essentially all we need from the discrete variable part to do quantum physics. So you see, it's just a bunch of definitions and some theorems that we used here. In the next session, I'm going to continue the theory of probability, but this time for continuous variables. So that will also be a short sort of a short session. And once we complete that, then we are completely prepared to delve into quantum physics. All right, and as always, I mention this at the end of my videos. The universe is meaningless from a scientific perspective, of course, and it is up to us to give meaning to it. Some people prefer assigning meaning to the universe through their religion. Some people prefer philosophy. Some others are find some spirituality in the world. But scientists, the good scientists, tend to investigate nature, not to assign a meaning to it, but to find out how it works. And believe it or not, the scientific method is the only credible method of gaining insight and understanding our awesome universe. So thank you very much for paying attention to this lecture. If you have any questions about the content of this lecture, please leave it in the comment section. Don't forget to subscribe to this channel, and if you like the videos, press the like button. And until next time, take care of yourselves, and remember always to be curious. Have a great day or night, depending on where you live, and until next time, bye-bye.